So, when should we use an Inception V3 or MobileNet retrained model on mobile devices? This question is crucial for developers as they figure out which model to implement in their applications. The decision between these two models really depends on your project's specific needs, especially when it comes to accuracy and speed. In this video, we're going to dive deeper into how to evaluate the performance of both models and see how to decide which one fits various use cases. So far, we've compared the performance of Inception V3 and MobileNet, shedding light on the trade-offs between accuracy and resource consumption. We've also looked into the retraining process for MobileNet and discussed how quantization impacts the efficiency of models for mobile applications. Through practical examples in TensorFlow, we've set up and tested these models, highlighting the importance of selecting the right model based on your project requirements. Moving forward, we'll focus on real-world applications and different optimizations to deploy these models effectively. Let's kick off with a fundamental understanding of the Inception V3 and MobileNet models. Inception V3 is a well-known architecture specifically designed for larger-scale datasets. It combines various convolutional filters in parallel at each layer, which allows it to learn richer feature representations. Now, because of its depth and architectural complexity, Inception V3 usually yields higher accuracy, especially in intricate image classification tasks. However, that complexity also means it has a hefty resource requirement, consuming a substantial amount of memory and processing power. This makes it less suitable for mobile environments, particularly older or less capable devices. On the flip side, we have MobileNet, which is optimized for mobile devices right out of the box. It's specifically engineered for edge computing environments, achieving comparable accuracy in image classification, but with significantly lower computational resource consumption. This is made possible through depth-wise separable convolutions, which essentially break down convolutions into a two-step process. This results in fewer parameters and less computational overhead. For instance, while Inception V3 has over 25 million parameters, MobileNet can achieve similar classification accuracy with as few as 4 million parameters. You can see why it's a fantastic choice for mobile applications. Now, let's implement the command to retrain our MobileNet model using TensorFlow. In this command, we'll specify the output paths for the retrained model and its corresponding labels, which makes it easy to retrieve and use later on. The -output graph parameter is key here, as it designates where the trained model will be saved, while the -output labels identifies the file that contains the class labels corresponding to the model's output. Next, we'll indicate the directory containing our training images using the -imagedir flag. It's really important that this path is accurate, as it points TensorFlow to the dataset you'll be using for retraining. The -architecture parameter is quite crucial too. Here, it specifies that you're utilizing the MobileNet variant with a size of 1.0 and image dimensions of 224 by 224 pixels, which is optimal for many mobile applications. Additionally, the -bottleneckdir option holds significance because it designates where to store bottleneck features. Now, these features are essentially condensed representations of input images that speed up training by allowing us to skip over redundant calculations. Overall, this command really streamlines the retraining process, letting you customize and optimize your MobileNet model swiftly. Now, let's see how we can implement the benchmarking of our quantized MobileNet model to evaluate its performance. To do this, we'll use the Benchmark Model tool provided by TensorFlow, which lets us assess how efficiently our model runs. The command starts with the path to the benchmark tool, followed by the .graph flag, where we specify the path to our quantized model file. It's crucial that this model has undergone quantization, which optimizes it for mobile inference. Next, we need to define the model's input configurations. The .input layer parameter indicates the name of the input layer, while .input layer shape specifies the expected shape of the input data. It's a 1 by 299 by 299 by 3 shape, corresponding to a single image resized to 299 by 299 pixels, with 3 color channels. Using .input layer type, we declare the data type of the input layer. For MobileNet, this is typically float. Now, we also specify the .output layer parameter to indicate where the model's final classified results are collected. The flags .showRunOrder, .showTime, and .showMemory set to false allow us to focus on the summary of performance metrics provided by the benchmark, which is essential for assessing how our model meets speed and efficiency requirements in a mobile context. Finally, setting .showSummary equals true ensures we receive a detailed summary of the testing results, which will help us make informed decisions about deploying our model. Now, let's implement the code for running inference with the MobileNet model in TensorFlow Lite. First, we create an instance of the interpreter, which serves as the interface for running the model. By calling the loadModelFile method, we load the trained MobileNet model that we converted into TF-Lite format. This step is really crucial, as the model needs to be in a compatible format to optimize performance on mobile devices. Once the model is loaded, we also need to initialize a two-dimensional array called result, which will hold the inference results. Here, num classes represents the expected number of output classes your model can predict. It's important to make sure this variable is set appropriately because it defines the size of the results array. Now, moving on, we execute the run method. We'll pass in the pre-processed input data and the result array. So, this method executes the forward pass of the model using the input data and fills the result array with the predicted class scores. It's crucial to remember that for MobileNet, the input data must be properly pre-processed to match the model's requirements, including having the correct shape and normalization. Proper pre-processing is key because it ensures that the model provides accurate predictions based on the input. Now, let's implement quantization when retraining your MobileNet model to optimize its performance for mobile devices. By adding a _quantized suffix to the architecture parameter, you're essentially instructing the retraining script to apply quantization techniques. What does this do? Well, it effectively reduces the model size and enhances inference speed. This step is crucial, especially when you're targeting devices with limited storage capacity, as it compresses the model from approximately 17 megabytes to just around 5.1 megabytes. So, this reduction not only makes the model more accessible for deployment across various mobile devices, but it also improves the user experience by enabling faster inference times. And here's the beauty of it. By minimizing accuracy loss while achieving these efficiencies, quantization really becomes an essential strategy in deploying lightweight and responsive model applications. Therefore, incorporating this suffix when specifying the architecture ensures you're leveraging the full benefits of quantization, allowing your MobileNet to perform effectively in edge computing environments where resources may be constrained. Lastly, let's take a moment to discuss real-world applications. Both models, Inception V3 and MobileNet, can be applied to various use cases, from image classification in mobile applications to real-time object detection. Developers often gravitate towards MobileNet for mobile-focused applications, especially in areas like augmented reality, or AR, and instant image recognition features in consumer apps. Meanwhile, Inception V3 shines in back-end processes where accuracy is paramount, such as photo tagging and sorting within online platforms. Ultimately, your decision should take into account the nature of your application. If you need quicker responses with a slight trade-off in accuracy for mobile devices, go for MobileNet. However, if the highest accuracy is non-negotiable and resources aren't a concern, then Inception V3 would be the way to go. Now, in conclusion, the journey doesn't end here. As you continue to learn and explore these models, remember to assess their performance in your specific context. Analyze the trade-offs, experiment with optimizations, and most importantly, keep the user experience front and center in your development. Thank you for tuning in, and I hope you now have a greater understanding of how to evaluate and implement the Inception V3 and MobileNet models. Be sure to subscribe for more deep dives into TensorFlow and machine learning.